In this video, we will introduce our work, Seeing Electric Network Frequency from Events, in which a simple yet robust event-based electric network frequency estimation method, ENF, is proposed. Electric network frequency, ENF, is the power transmission frequency in the grid, whose nominal value varies according to different local standards, 60 Hz in most of the Americas and 50 Hz in most rest of the world. ENF fluctuates within a small range around its nominal value due to power supply and consumption imbalances, exhibiting noticeable regional and temporal variations. A light source connected to the power grid flickers at a frequency twice that of the electric network frequency, ENF. This flickering causes light-dark variations in illumination that are imperceptible to human but can be recorded by cameras, thereby enabling the estimation of the grid frequency. This work introduces a comprehensive event-based framework for electric network frequency, ENF, estimation. We first demonstrate that ENF can be extracted from a new modality provided by the so-called event camera, and thus introduce a method, ENF, for estimating ENF from event streams. The proposed ENF showcases superior estimation performance on the first event video hybrid dataset we created. Existing video-based ENF, V-ENF, extraction methods attempt to recover light flickering by averaging the pixel intensities over video sequences. However, due to the inherent properties of conventional cameras, existing V-ENF extraction methods still face a series of challenges. Summarized as follows. In this work, we attempt to tackle these challenges by leveraging event cameras. Event cameras record data in a completely different form compared to standard cameras that simultaneously record the absolute intensity of pixels at a fixed frame rate. An event camera acts as an asynchronous sensor, each pixel of which responds independently to changes in pixel intensity and generates events to record the changes. An event is triggered if the log-transformed pixel intensity difference at position x exceeds a predefined threshold c at time t. This unique form of visual information recording endows the event camera with the advantages of high temporal resolution, high dynamic range and low latency. In the case of ideal sinusoidal light flicker, the intensity of the pixel follows a sinusoidal pattern. The event camera employs log transformation and threshold comparison on the pixel intensity, enabling the capture of not only the fundamental frequency of the flicker but also its harmonic components within the event stream. Additionally, due to the unenclosed nature of the light flickering, the resulting events exhibit a consistent instantaneous polarity. Unlike common motion where events of both polarities are simultaneously generated in similar proportions. The event-based ENF, E-ENF, method comprises three stages. In the temporal sampling stage, the event stream is converted into event slices by artificially sampling the event stream based on the chosen sampling interval, denoted as delta t, in the above process. Asynchronous events are framed into uniform time intervals. During the spatial sampling stage, by extracting the most frequently occurring polarities in each time slice, we convert the time slices into a one-dimensional polar sequence E-N, with a fixed sampling interval. This sequence accurately represents the variation of illumination, transforming the previously inconsistent polarity and position into a standardized polarity representation. Finally, the polar sequence E-N is analyzed using a short-time Fourier transform, STFT, and peak search to obtain the corresponding dominant time frequency variation at each harmonic component. The final estimation result is obtained by fusing each harmonic through some absolute first-order difference criteria. To evaluate the proposed ENF method, we construct the first event video hybrid ENF dataset, EVNFD, containing both events and videos recorded in real-world environments with static, dynamic and extreme lighting conditions. EVNFD contains a total of 51 sets of data. Each set of data contains 2 video sequences and 1 event sequence. We conducted comparative experiments on the EVNFD. In dynamic and extreme lighting scenes, the performance of ENF drops dramatically compared to static scenes. Compared to the V-ENF method, the proposed ENF estimation method exhibits stable performance in static scenes and demonstrates significant advantages in challenging scenes involving motion and extreme lighting conditions. Thanks for watching. More information and details are in our paper and project page.